Hello everyone, I'm Won Lee. Today's topic is central limit theorem. It is very important key theorem in statistics. If you do not know central limit theorem, you have nothing about statistics. I dare to say like this. All right. Before going to central limit theorem, a little review about samples and its sample means distribution. Okay, I told you this one is a sample. It is a theoretical, say, sample. Okay, capital letter, nothing but capital letters. We used to sample like this, small letters. Small letters sample is obtained value. Okay, this capital letters sample is random variables, consist of random variables. And x1 up to xn, IID f of x. F of x means population probability distribution function. So keep in mind anytime this kind of a thing. And I told you distribution of x bar last time. So x bar is also what? Random variables. So x bar has some distribution and x bar has mean and variance. Okay, I explained it with this simple example. This is a real simple example. And the mean and the variance of x bar is like this. Mean of x bar is population mean, mu. Variance of x bar is population variance over n, something like this. So it these are basic thing to go further. Okay, let's go to central limit theorem. We use CLT, okay? CLT. Central limit theorem states that it is not difficult, regardless of distribution of a population X. Same thing, whether we know the distribution or not, whether we know f of x or not, right? Population, there is population, random variable x. Random variable x has distribution. Its distribution is f of x. So we do not know what f of x is, okay? If sample size is sufficiently large is n sample size greater than equal to 30. We used to this size n greater than equal to 30. It was found empirically. So just you get it. The distribution of a sample means x bar, right, approaches a normal distribution. In other words, f x bar follows normal distribution. What mean? Mu, population mean, variance, population variance over n. So it is very short and not difficult one to understand if you understand capital letters, okay, sample. If the population follows a normal distribution, okay, follows a normal distribution, then x bar is normally distributed regardless of the sample size, whatever sample, n equal to 5, x bar follows exactly normal distribution, right? Because x1 up to x5 follow normal distribution. Central limit theorem is a fundamental theorem in statistics that can be proven. In mathematical statistics, we prove this result. It is not an exaggeration to say topics we will cover going forward, including estimation, chapter 4, hypothesis testing, chapter 5, and from chapter 5, we will uh, deal with analysis method, such as ANOVA, analysis of variance, and the regression, are all developed under the framework of a central limit theorem. That's why central limit theorem is a key theorem in statistics. Example, suppose a certain population X, okay, has a mean 10, standard deviation 2, and follows some distribution. We do not know the distribution function, f of x, whatever. From this population, if a sample of size 36, n equal to 36, obtained, what is probability of x bar between 9.5 to 10.5? X bar in this case, approximately normal distribution. Okay, so we standardize it. X bar minus 10, it's mean 10. Standard deviation 2. So 2 over square root 10. Square root 10. Then 9.5, same procedure. 10.5, same procedure. Then G. This one comes to G, standardized normal. Left hand side minus 1.5, right hand side 1.5. Then the probability is 0.8664. You know how to read this one. Normal distribution. From 0 to 1.5 here, the probability is what? 1.5. 3, sorry, 0.4332. So minus 1.5 to plus 1.5 is 2 times 4.332, right? If the sample size 64, this case 64, is obtained, what is probably same probability x bar from 9.5 to 10.5? Then standardize it, left hand side, right hand side. What is difference? Difference is different from above. I mean, in this case, number one, 36, the sample size increases 64, right? So this part will be changed. So this one is minus 2.0 plus 2.0. So what is the probability of that? Now here, this one is 2, then what is the probability? 2.0, 4772. So multiplied by 2, it is 9544. Okay, bigger than this. It will be related to what? Interval estimation, chapter 4, but you just see this result. Okay, so want to get same probability, x bar of x bar, but sample size different. In the case, it is bigger than, the probability is bigger than that. Okay, okay, let's wrap up central limit theorem. This diagram shows distribution of x, population distribution, right? X. And the shapes of distribution of x bar based on different sample sizes. Okay, let's see this one. Distribution of x is what? What is this? Uniform distribution. You don't have to name a distribution, but it is one of the probability distribution function, f over x. Then x bar, distribution of x bar when n equal to 2, sample size 2. Oh, triangle. Okay? Distribution x bar, n equal to 5. It some a little smoothed triangle. What is distribution of x bar when n equal to 30? It's the likely normal distribution. When the population has distribution of this way, okay, this distribution, then n equal to 2, this shape, little like ice cream, and n equal to 5, it becomes to this way. And n equal to 30 from this population, okay, it is a very, very likely normal distribution. When the population distribution is like this, then n equal to 2, distribution of x bar is like this. Okay? And n equal to 5, like this. What is this? Skewed to the right, a little skewed to the right. When n equal to 30, this way, distribution of x bar is these three are almost normal distribution. Okay, get it? So if you have population, you think about distribution of population, distribution of x is a little like, this way. Okay, it is not normal distribution. Then n equal to 2, it is very nearly normal distribution. And n equal to 5, then very much likely normal distribution. N equal to 30, just normal distribution, like this. Okay? The distribution, shape of the distribution will change, depends on the size of a sample. Okay? That this diagram shows you central limit theorem can be explained. I think this kind of result from simulation. Okay, believe it. Okay, thank you so much. That's it today.